is a transistor in which this gate terminal is controlling the current from source to drain or drain to source. Basically, current between these two terminals is being controlled by the gate terminal. And this is the characteristics of the MOSFET. And what we saw was that a small change in the gate terminal can produce a huge change in the drain current. So that's why we can achieve amplification. At the same time, the gate can switch off the channel. If you recall our previous discussion, that this transistor conducts uh, only when there is an inversion layer, and that inversion layer is because of the gate voltage. The BJT operation is pretty much like a PN junction or two PN junctions in series, and that's how we can also understand the IV characteristics of the BJT. Okay. So with this discussion on electronic devices, the next thing that we discussed was integration, or putting many electronic devices in a single chip.
Sorry to interrupt, sir. Sir, can you please
Yeah.
make everyone attendees? Someone has removed me from the meeting.
Uh, Everyone attendee. Okay. Somebody removed you from the meeting?
Yes, sir.
Okay, let me do that. Yeah, so please don't do these kind of things. Just a moment. Okay, I hope this would be all right now because I changed the permissions. But if you can tell me who is doing that, I can take some action against
Sir, so
those
that
actually.
is not shown. Only it's shown that someone removed you from the meeting.
Okay. Yeah, so if I find out a person who does this, that can be a there can be a good amount of penalty on that guy. Okay.
So this happens in other lectures also.
Sir, it usually happens in math class.
No, it always feels good to do something like this. But given the limited time, it's not. So these kind of things should not be done in the class. You can do these kind of things at other places. Okay. So I hope it should be all right now. Yes. Now I hope you can again see the slides, and can anyone please confirm?
Yes, sir.
Yes, sir.
Yeah. So after the devices, we also saw how do we consider these electronic devices and circuits, because ultimately these devices are we make circuits out of these devices, and the diode is I would say is the most one of the most common devices which is used in many at many places in circuits, and this is the ideal diode circuit model. So this is the diode IV characteristics. In forward bias regime it conducts, in reverse bias it does not, and this is equivalently understood as like this, that for a forward bias the diode is like a short circuit, and for a reverse bias it is like an open circuit. Okay, so this is the diode equivalent or ideal diode equivalent for circuits. More realistically, this is how the diode should be uh, represented, that uh, after or above cut-in voltage, the diode behaves like a short circuit, and below cut-in voltage, the diode is like an open circuit. And as all of us know by now that one of the most important applications of the diode is AC to DC conversion, which is used at many places, because AC is generally the choice. AC is transported over long distances, but many electronic appliances work on DC direct current, and so we need this kind of conversion at many places. And diode is one of the prime devices that is used to do that. So there are two ways to do that. One is the half wave rectification, and this is the electronic circuit to convert AC into a DC signal. We have a diode and a resistor. The output is taken across the resistor, and if you just replace this diode with this kind of equivalent circuit, in that case you would see that if there is an AC signal at the input terminals, in the positive half cycle of the signal, the diode will be like a short circuit, and exactly the same signal will be at, at the output across the resistor. So in the positive half cycle of the signal, the output will be same as the input signal. In the negative half cycle, however, the diode will be like an open circuit. It will not conduct, and the output will be zero. So this is the output signal across the resistor when we have a diode. And if we calculate the average value of this signal, output signal, which is also the DC value of the signal, it turns out to be 0.318 Vn, where Vn is the maximum uh, amplitude of the wave. The average value of an AC signal, or the DC value of this AC signal, is 0. So the DC signal or the average value of the input signal was 0, but the average value of the output signal is now non-zero. It's a positive value. So that's how we have achieved some net DC voltage at the output. However, this is being achieved at a cost of losing the negative half cycles of the input. And in order to do that, uh, full wave rectification is done. And this is the kind of circuit that is used in full wave rectification. This is one of the most popular full wave rectification circuit. So if you have a close look, in the positive half cycle of the input, these are the input terminals, essentially these 2 points, and the diodes are connected in this rectangular fashion, and there is a resistor bridge uh, between the diodes. So in the positive half cycle, as you can see, the positive voltage is there on this terminal, the negative voltage is there on this terminal. So which means that this diode, D2 diode, will be short circuit because this is forward biased. D1 is reverse biased because this is the N terminal of the diode and there is a positive voltage. So this will be open circuit. There is negative voltage here, so this D3 will be short circuit and D4 will be open circuit because this is reverse biased. So this will be the equivalent circuit, and as you can see that the output voltage is taken across the resistor, and the polarity of the output voltage will be such that this part of the resistor is positive, this part of the resistor is negative. Okay, so a positive voltage is here, negative is here, and we get the same kind of output across the resistor as there is this positive half cycle. Similarly, in the negative half cycle, what happens is now the negative voltage is at this point, positive voltage is at this point. So this is the equivalent circuit. If there is a negative voltage at this point, the diode D1 will be forward biased and hence short circuit. D2 will be reverse bias and therefore open circuit. Similarly, D3 open, D4 short. And this is the equivalent circuit diagram in the negative half cycle. And if you see closely the output across the resistor, it will be again same as the input, but now the polarity of the output is again exactly like the input voltage. This terminal of the resistor is negative, this is positive, because this terminal is connected to the positive voltage, this is connected to the negative voltage. So essentially the output uh, is again the same as it was in the positive half cycle. So what we have done is, using this kind of circuit, we have converted this AC signal into this kind of signal in which this negative half cycle has been inverted. The positive half cycle is the same, but the negative half cycle is inverted.
Excuse me, sir.
Yeah.
Sir, someone is again removing Anisha's messaging.
Sir,
Okay.
someone
Yeah.
again removed me, and sir, my mic
Okay.
was also disabled.
Yeah, but I changed the permissions as well. Let me see. Do you know where should? Oh, okay. Now I can see more permissions. Uh, no, there is some problem with the with this MS Teams because sometimes it shows settings and sometimes it does not show. So what I'm doing is do you know who is doing that? Anybody has an idea who's doing that?
No, sir, it cannot be known. So this is a fault of
Yes,
MS
yeah.
Teams.
Actually, MS Teams is not a very good video platform to do these kind of things. Zoom or even WebEx is better. So anybody else would also Just give me a few moments. Yeah, so now everyone is attendee, and I hope that nobody would be able to. Arnav, you have a question?
No, sir.
Yeah, so now everybody is an attendee.
Thank you, sir.
Okay, so let's come back. Uh, so as you can see that in this full wave rectification in which we are rectifying the entire AC wave, we are not losing the negative half cycle. The average output or the average value of the output signal is now around 0.6 times the maximum value. And if you remember, the average value of the output in the case of half wave rectification was around 0.3. So now the DC strength of the signal has been increased, has been actually increased to twice. Okay. So just a moment, somebody is. Yeah. But still, as you can see, there are a lot of ripples in the output here. Still, the output is changing a lot, actually. Okay. So what is done is, in order to reduce these ripples, in this circuit, in addition to these diodes, we also put a capacitor and resistor like this. And if does anybody know what is the function of a capacitor? What does a capacitor do essentially?
It
So it
stabilizes
stores
the
energy.
output.
And why does it do that? How does it do that basically?
Sir, it gets charged in one cycle and gets discharged in another cycle.
Yeah, that is true. But how does it do the stabilization?
So it stores the energy in the electric field inside the dielectric, and when there is no outside supply, so then it supplies the circuit with the stored energy.
Yeah, those things are true, but the main point here is that the capacitor cannot be charged instantaneously. It takes some time to charge the capacitor, and that time is known as the charging time. You might recall that from your previous studies of the capacitor. And what happens is that when the input changes like this, the output does not exactly follow the input. There is some delay in following the input, and so this is the output that we obtain here. And if we connect the capacitor, initially the capacitor tries to follow the input, but there is a delay, and as soon as the voltage across the capacitor is going down, the input again increases. So the capacitor voltage does not go down up to this point. up to the point that is there in this, the minimum point in the output voltage. And this is the kind of voltage that we see across this capacitor. So is this part more or less understandable? This is because that the capacitor cannot be charged instantaneously. It tries to follow the input, but as soon as it goes down, the input again increases, and again the capacitor voltage increases. Okay, so this is the waveform when we have a capacitor connected in addition to this kind of circuit. And as you would expect that now the DC voltage is pretty high. Now it is around 0.9, or actually depends on the value of the capacitance and the resistance, the load resistance essentially. Okay, so this is these are among the most important uses of the diodes. And similarly, these rectification circuits are also known as the clippers. Clippers because they can clip a certain part of the waveform. And the circuit that we used for half wave rectification, this circuit essentially, this can be used to remove the negative half cycle of the input waveform. And uh, in addition to the diode, if we have any voltage source as well in the circuit, then we can take that into account. We can apply the KVL in the positive half cycle and the negative half cycle and obtain the output waveform. So I'll share this slide with all of you, and I have put these examples on the slide. What is the circuit and what is the input voltage and what is the corresponding output voltage. So all these things can be pretty easily understood if we understand the basic KVL in these circuits and if we understand the ideal diode model. So please remember that in most of the cases we are assuming the ideal diode model. And what does that say? That whenever the voltage on the P terminal of the diode, this arrow sign is positive, this point, if the voltage is positive, the diode is short circuited. And if the voltage is negative here, the diode is open circuited. Okay, and similarly, when the voltage is positive on the N terminal, the diode is reverse biased, open circuited. And when the voltage is negative at this terminal, the diode is forward biased and short circuited. So this is the circuit, this is the input voltage, and this is the corresponding output voltage. So I am just leaving this for you to figure out. And if there is any question, you can write down an email to me or to the TAs as well. Okay. Similarly, there is this circuit known as the clamper circuit. And what is a clamper? Clamper means that it can clamp the signal to a different level. So if this is the waveform, then it can change the DC level, or it can clamp it to a different DC level. So we will obtain exactly the same kind of signal, but now the signal, uh, the signal direction will be, or the signal DC level will be changed. It is as if we have shifted the signal down by this voltage V. Okay, and the clamper circuit looks something like this, in which we have a diode and a resistor in parallel. And in addition, there is a capacitor as well. And this capacitor is actually, initially, it is considered to be the ideal capacitor, which can store the charge in the circuit. And uh, so what happens is that in the positive half cycle, the capacitor stores the charge, the diode is short circuited. So the output voltage, which is taken across the resistor, also across the diode, is 0. But in the negative half cycle, the applied voltage is negative and the capacitor voltage is positive on this terminal, negative on this terminal. So in this half cycle, what happens is that this capacitor acts like another battery of the same voltage, and the negative voltage is now the twice of the input voltage, because V is coming from the battery and another V is coming from the capacitor. And again, we are not considering the, so generally the capacitor has an exponential decay and exponential charging and discharging profile. We are not considering that. We can, in practical cases, we would need to consider those things as well. Okay. So this is a clamper circuit. Again, for negative and positive half cycles, I would recommend all of you to see how the inputs and outputs are changing. So, so please go through that on your own and try to understand. If there is any question, I can talk to you about it. Now, in addition to a simple diode, we can use the Zener diodes as well in various circuit applications, and these are known as the voltage regulator circuits. And as you can see, there is this Zener diode has a different kind of symbol. Uh, a symbol like this, in which the other terminal is slightly tilted. And what happens is that if we apply a certain voltage, let's say this voltage is changing from 0 to 60 volts and then to minus 60 volts. So what this circuit does is that as soon as the voltage goes above 20 volts, which is the Zener voltage of the diode, in that case, uh, this Zener breakdown happens, and this this is the voltage does not increase further. So 20 volts will be the maximum voltage which uh, that this Zener diode will tolerate across it. In the positive half cycle, the Zener diode is reverse biased, and above minus 20 volts or about 20 volts, the Zener diode will only allow 20 volts to appear across its terminals. So this system is now sort of protected because of the Zener diode. So whenever we are not sure about the voltage fluctuations in the supply and we want to protect our system, our electronic appliance, what we do is we put a Zener diode in parallel to the system. And whenever the voltage crosses the Zener voltage limit, the Zener diode does not allow the voltage to increase, and the access current flows through the Zener diode. And the system is now protected because the access current is now flown through the Zener diode. And in the negative half cycle, so what happens is in the negative half cycle, okay, so in negative half cycle, we have a positive here. So this is open circuited, and there is no current in the circuit. So this is essentially the output, and this is, I would say, this is exactly not the output. The output would be, yeah, this is the output. This would be the output across the system. So that way, even with a fluctuating supply, we are getting a constant voltage across the system of our interest. Okay. So with this, these are some of the applications of the diodes, and I'll share the slides today itself. So go through them again and let me know if there is any question. Now we come to a more important topic, which is the operational amplifiers. And in short, it is written as op-amp. Have you guys studied about op-amps earlier? Have you seen them anywhere?
No, sir.
Anybody?
No, sir.
No, sir.
Okay. Yeah, so op-amps are an extremely important electronic, I would say, electronic. Nowadays, they come in small ICs. They are very important circuits. And as the name suggests, let's try to understand what is an operational amplifier. So as the name suggests, it is an amplifier, which means it can amplify the signals. But transistor is also an amplifier. So what is new here? Okay. So we just do not want an amplifier. In addition to an amplifier, op-amp is also a device on which we can do various operations. And that's why this operational amplifier is the name of this IC, essentially. Okay. So op-amp is an IC that uses external voltage to amplify the input with very high gain. And this operational term in the name suggests that we can perform various mathematical or logical operations on these amplifiers. So as you can see, we can add signals, we can subtract signals, and we can integrate signals, we can differentiate various signals. So we can do various kind of mathematical operations on these circuits. And as you would realize that since we are able to do various mathematical operations, these are extremely important part of computers actually, especially during earlier times actually. So nowadays, most of these operations are being done digitally, as you would see in digital electronics in your second year. So nowadays, op-amps are not so frequently used in computers, but the early day computers were mostly based on op-amps, and these were the circuits actually, the important circuits in the electronics. So these were also the circuits that were investigated in the beginning, and they are still used. So wherever we need analog kind of computation, wherever we need to perform various kind of operations on analog signal itself without converting it to a digital signal, in that case, op-amps are used. And this is an active circuit element designed to perform various mathematical operations and logical operations as well. So these are some of the most popular op-amp ICs. One of the ICs is LM111, LM324, LM741. These are the name of the ICs, and LM stands for linear monolithic. Linear monolithic means that it is on the same piece of semiconductor. We are not using different pieces of semiconductor, and it's a linear fabrication. It's a linear kind of circuit. Okay. So this LM741 is the most common op-amp, and this is the schematic diagram of this op-amp, as you can see. So as you can see, this looks quite complicated. There are various transistors. There are many transistors, in fact. And this was based on BJTs, actually, because initially the BJTs were discovered in the beginning, and people were trying to make computers out of BJTs, and op-amp was one of the most important constituent there. This is the op-amp circuit. And understanding this circuit actually needs more, I would say, more technical knowledge of transistors that you would only obtain in your coming courses. That is not sort of in this, we don't have that much of time in this course. So what we do is we try to understand op-amp as a black box. And let me tell you something that even now, questions are asked on op-amps, about op-amps, even in your internship tests and even in your placement tests. Also, generally, for an electronics graduate, everybody try to see if you know op-amp or not. Basically, op-amp are one of the most basic stuffs in EC, electronics and communication engineering. So it's good to know, it's expected that you guys would know about op-amps. So this is the circuit. Generally, nobody asks about circuit diagrams of the op-amp because there is a lot more about beyond the circuit diagram. So this is how this IC looks like, 741, and there are 8 pins in this. As you can see, these are 741 ICs, and 4 pin on one side, 4 on the other side. Okay, and this is the pin diagram of this IC. And as you can see that this pin 1, so the way these pins are numbered in the IC is this: 1, 2, 3, 4, 5, 6, 7, 8. This is the general convention whenever we number the pins in any IC. Okay, so if you come across any IC and somebody asks you where is pin number 6. So you need to count like this, okay? And this point, this dot here, or this kind of dot, it shows that it is the top of the IC. So we need to see from that side. On the left side, 1, 2, 3, 4, and then from the bottom, 5, 6, 7, 8. And you might have guessed by now that why this name 741 is there. The 741, because if you see that on pin number 7, pin number 4, and pin number 1, on 7 and 4, we connect power supplies essentially. And pin number 1 is the pin which ensures offset null. So we'll come across this. So these 3 pins are quite essential and in operation of this IC, as we will see quite soon. And that's why this is generally numbered as 741. This is one of the ways in which early initial days ICs used to be named actually. So DC power supplies are connected on 7 and 4th pin, and offset null is, what does it mean? It means that it tries to, so there are 2 input terminals. Pin number 2 and 3 are the input terminals, and pin number 6 is the output terminal. Pin number 8 is just extra terminal, nothing happens there. So 2, 3, and 6, these 3 pins are the pins that we use in our circuits actually. So ultimately, the op-amp is a 3-pin device, or 2 input, 1 output terminal device, and that's how we generally denote an op-amp. There are 2 input terminals and 1 output terminal. So pin number 2 and 3 inputs, pin number 6 is output. Pin number 7 and 4 are the bias terminals. So we need to put constant DC supply there to properly bias these circuits. And now let's come back to this pin number 1, which is offset null. And what it does is that it always tries to make sure that the voltage difference between these 2 input terminals is null, or the offset voltage is null. So this is like a compensator. This pin number 1 tries to make sure that the voltage difference between the 2 input terminals is always 0, or as close to 0 as possible. So in summary, op-amp is an IC. It has a complicated circuit. We only use 3 of these pins. It has 8 pins, only 3 pins. Out of these 3 pins, 2 are the input terminals, 1 is the output terminal. And the 2 other pins, pin number 7 and 4, are the DC supply pins. So we generally put a DC supply there and just leave it. We don't think much about it. And pin number 1 is a special pin which tries to ensure that the offset voltage, or the voltage difference between pin number 2 and 3 is 0. It's null. Okay. Any question on this right now?
So what is the function of pin 5?
Pin 5 again, sorry, it is like pin number 1. It's also offset null. So these two terminals are offset null. Now you would say that why is this name 741? Yeah, it's just a matter of choice. Okay.
So what is the function of pin 8?
It's not connected. It's there just to keep a symmetry actually. So it's not needed at all. Okay, so it is just a pin. It is not connected to the circuit inside it. Only 7 pins are connected. But in order to make a symmetric integrated circuit, we need to have 4 pins on both sides. We cannot have 4 pins on one side and 3 on other side. That will not. That is not a good structure for handling. Actually.
So what is inverting and non-inverting input?
Yes. Yeah. So we are coming to that. These are the 2 input terminals. One is known as the inverting input terminal. Second is known as the non-inverting terminal. So as you might have noticed that this non-inverting input terminal has a positive sign corresponding to it, and a non-inverting, inverting input has a negative sign. As expected, inverting means that it inverts if any input is applied on this terminal, the output will be the inverted waveform like this. So if we apply a waveform like this on non-inverting terminal, positive terminal, output waveform will be the same, but it will be just an amplified output. Okay, because it's an operational amplifier, it is an amplifier. So a small signal on the inverting terminal will be the same in shape, but just amplified. On the other hand, on the non-inverting terminal, the input is inverted. The positive half cycle is converted to a negative half cycle, and negative half cycle is converted to a positive half cycle. So which means that a 180 degrees phase difference is introduced if the voltage is applied on the non-inverting terminal. Okay. Yeah, so please also keep in mind that always the voltage uh, offset is there. So this is the internal circuit diagram. Generally, this is how it is expanded, that these V1 and V2 are these two terminals. On the internal side, this is how the op-amp is modeled, actually. So the actual circuit diagram is this, and equivalently, it is written like this. So equivalently, what we can say is that op-amp is uh, on the input side, op-amp has an input resistance Ri, and this resistance, also known as input impedance, this impedance is extremely high. So for ideal op-amp, this Ri is infinity, almost should be infinity. Practically, it is in mega ohms. On the output side, we have a voltage controlled this voltage source which is dependent on the input voltage. So this is voltage dependent voltage source. And so the if the input voltage is Vd, which is essentially the difference between the two terminals, the output voltage will be A times Vd. So this is a voltage source, but it is dependent on the input voltage. So that's why it is known as voltage dependent voltage source. And then this op-amp has an output impedance, output resistance as well. In ideal case, this RO is 0. So generally, these are the op-amp parameters. One is the open loop voltage gain, A. Open loop means that the input terminals and the output terminals are not connected to each other. This is an open loop. And A is the open loop voltage gain, input resistance Ri, output resistance Ro, and supply voltages, which we generally don't discuss. So in ideal cases, the voltage gain is infinity, which means that it is an extremely high gain amplifier. Input resistance is also infinity. Output resistance is almost 0. And supply voltages we generally don't consider. But these are the typical ranges in circuits that we have. The voltage gain is maybe 100,000, or it can be around 1,000 as well. So it's around 1,000,000 or so. Input resistance is in mega ohms or even larger than that. Output resistance should be 0 ideally, but it is few ohms. And if you compare this with input resistance, it is as good as 0 actually. Supply voltages is either plus minus 12 volts or plus minus 5 volts, and in some cases it is also plus minus 30 volts. So this is the equivalent circuit, but we don't need to, if somebody asks you what is the equivalent circuit of op-amp, this is the full circuit diagram. This is the equivalent circuit diagram. But generally, even we do not need to care too much about it. What we need to care about is these things. The internal circuitry in the op-amp tries to force the voltage at the inverting input to be equal to the non-inverting input. So what it means is that the op-amp internal circuitry is such that the voltage on these two pins, pin number 2 and 3, basically inverting and non-inverting terminals, is equal to each other. Tries to force these two voltages equal to each other, and that's what is actually shown by this offset null. These 2 points are such that they tries to nullify any offset between 2 and 3, any offset between inverting and non-inverting terminal. And if there is an offset, so let's say we are not able to make a circuit in which the offset is absent, then we can apply some voltage on these pins, pin number 1 and 5, and we can make this offset again 0. The voltage difference between the two terminals 0. So externally also we can do that, but in an ideal op-amp, internal circuitry is such that it offsets any voltage difference across the inverting and non-inverting terminal. So as a consequence of that, because of high input resistance, so this is like a very high input resistance in this side, ideally no current flows into the either input terminal. So if you see op-amp in any circuit in electronics, no input current flows inside the op-amp, right? Which means that because there is no voltage difference, the resistance is also infinity, so no input current is there. Also, a direct consequence of that is that no current flows out of the output terminal. So this op-amp, this side, no output current flows. Okay. Now you would ask, if there is no current which is going inside this triangle and no current which is coming out of this triangle, then why is this useful or how is this useful? You might have that question. Yes or no? Do you have that question or not?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yeah,
Yes,
so
sir.
yeah, we'll see that. You will see that. So, but please, if you need to remember anything about the op-amp, remember these 3 points. That in an ideal op-amp, there is no difference between the voltage at positive terminal and the negative terminal. Between these two terminals, the voltage always remains the same. And no current goes inside the triangle, no current comes outside the triangle. These 3 things, just remember these 3 things and you would be able to solve any circuit of op-amp actually. Okay, you don't need to remember any circuit diagram, equivalent circuit diagram, but these things are good to know because otherwise it's just like memorizing things. So now let's see how do we use op-amps in electronic circuits. So the first use of the op-amp is the inverting amplifier. Inverting means we want an amplifier, but we want our signal to be inverted. We want the output signal exactly opposite of the input signal. So this is how we make the inverting amplifier. And so if there is an AC input here, what would be the output voltage?
So amplified and inverted.
Yeah, and why do you think so? So for example, if this is the input voltage, so please remember these 3 points. 2 points are no current flow inside the triangle and no current flows outside the triangle. Third point is that always the output the voltage at these 2 points are always the same. So what it means is that one of the terminals is grounded, voltage is 0 at positive terminal. So the voltage will be, so it is as if this terminal is also grounded. So the voltage is 0 here as well. Okay. So what happens is that there is an input voltage, and because of this input voltage, some current will flow. But this current cannot go inside the triangle, so all of this current will go to this part of the circuit, and no current can come out of the triangle, so this current will go to the output side. Okay, what is this current? This current is the current that flows here. The voltage here is 0, here it is Vn, so the current is Vn minus 0 by Rin. Okay, and the same current is flowing through RF. So the voltage difference that it produces is I times RF. So the voltage that it produces across RF is RF times V in divided by Rin, and that is essentially the output voltage, because the output voltage is if you do KVL, the output voltage will be the voltage across RF. So the V out will be equal to minus RF by Rin times V in. And if, for example, Rin is, let's say, few ohms and RF is few kilo ohms, let's say it is 10 ohms and it is 10 kilo ohms, RF by Rin will be 1000, and there is a negative sign. This is a consequence of the KVL. So I'm not going into the exact details, exact circuit analysis here, but I would like all of you to do this circuit analysis. So the output voltage will be the negative of the input voltage times 1000. So it is an amplifier as well as inverted signal.
Excuse me, sir.
Now, if there is a question, yeah.
Sir,
Sir,
we
if
said
we
that
take the RF, sir, if we take a RF less than Rn, then it will not be amplifying.
Yeah, it will not be an amplifier. In that case, it will be de-amplifier. Sort of.
so, sir, why we said it is a property of op-amp? Because
No, it is not a
our
property
choice.
of op-amp. Yeah, it is. Yeah, you are right. This circuit is very simple. So what op-amp is doing is, yeah, I guess you are not getting that subtle point. What op-amp is doing is, so you can say that we can just take output across RF and uh, we can ground this and take the output across the RF. Is that what you're saying?
No, sir, I was asking that you said that in op-amp there is a very high gain, but here there is no function of op-amp but only choice of
Yeah.
resistors.
Yeah, so we are not using the internal gain of the op-amp in this circuit. In some cases, we use that also. But still, why is op-amp needed in such kind of amplifier? You might ask that.
Yes, sir.
The thing is that op-amp input impedance is extremely high and output impedance is extremely low. So generally, what happens is that generally we have an electronic circuits which give us input voltage, and we need to connect that electronic circuit, the previous electronic circuit, to a different electronic circuit, and in that case we need to match the impedances, because if the impedances are not matched, in that case the current can increase a lot. So in order to do that, this op-amp circuits are used, because if the output impedance of an electronic circuit is extremely high, then op-amp is used for that purpose. Similarly, the non-inverting amplifier is the amplifier in which the output signal has the same shape as the input signal. And if you analyze this circuit in which input is being applied on the positive terminal, on the negative terminal, we have connected two resistances. One is grounded at the other terminal and one is connected to V out. So just remember three principles: that no current can flow inside the triangle, no can flow out the triangle, and the voltage at the 2 points will be the same. So if V in is the voltage here, V in would also be the voltage here, and in that case you can know what would be the V out. V out would be just R1 plus R2 divided by R1 times V, if you do basic KVL in this circuit. Okay, so I recommend all of you to do this KVL and KCL analysis. It's, if you remember these 3 points about the op amps, these 3 points, then it's just a matter of KVL and KCL. So the other use of op amp is a differentiator. Differentiator means that the output voltage is the differentiated form of the input voltage. And in that case, we need to use a capacitor. Again, remember the 3 points: no current in triangle, no current out of triangle, both of the terminals at the same voltage. So by doing the KVL KCL analysis, the output voltage will be minus RC times dV in by dVt. So output is RC times the differentiation of the input voltage. Why is that so? Because the current across the capacitor is I is C dV by dt. So the current across this capacitor will be C times dV in by dt, and the same current flows through this R, which is also the equal to the output voltage. So that's why the output voltage is R times C dV in by dt times minus. Similarly, integrator integrates the input signal. The output is equal to the integration of the input signal, and if you closely look, we just swap the positions of the resistor and capacitor. Capacitor now, so the capacitor is now in the feedback circuit. So this is known as the feedback circuit part, because this branch of the circuit is connecting the output to the input terminals. So that's why it is known as the feedback branch of the circuit. In this case, the feedback branch was resistor. In this case, it is the capacitor, and the output will be minus integration 0 to t V in by RC dt plus V initial. So just do the KCL KVL and you would find it out. Okay, let's move. I would recommend all of you to try out all these calculations and get back to me if there is any question. Otherwise, you might not understand this. So this is the summing amplifier. What do we mean by summing amplifier? That it's amount to an addition operation. So if we have many inputs, we need to have an output which is the addition of all those inputs. This is how we do it. And this is also an inverting amplifier, as you can see. But if we need to make a non-inverting amplifier, in that case, we can apply it to the positive terminal. Because what is happening is that the currents, because of various voltages, is getting summed up, and it is flowing through this feedback resistor RF. So that's why this V out is equal to minus RF, V1 by R1 plus V2 by R2 up to Vn by Rn. So if we remember those three rules, then all this is just the KCL and KVL. Similarly, the difference amplifier, in order to make a difference amplifier, we need to connect voltages at one voltage at the input inverting terminal and second voltage at the non-inverting terminal. And if you do the KVL, KCL, this is what we will obtain. So I would recommend all of you to do this actually. This is an interesting calculation. Okay. Now this is also a very important circuit component. This is known as the buffer or voltage follower. So what happens here is that V out is exactly equal to V in, because V out will be equal to this voltage and this voltage is equal to this voltage because of the op amp characteristics. But why do we need such circuit elements? Why do we need this kind of circuit elements in which V out is just equal to the V in?
Sir,
Anybody?
we do not want current in V out.
Exactly. Yeah, you're right. So the first thing is that if there is, we are obtaining V in from another electronic circuit in which there might be some impedance, there would always be some resistance. Then at the output voltage, or if we connect that to any another electronic circuit, the current might flow from previous circuit to the new circuit. And sometimes this current can be huge and it can burn out this kind of this next stage of the circuit. So in order to, as Dikshant pointed out, in order to avoid this current and just apply the voltage, we need buffer elements. These are also known as voltage followers, and these are very important circuit elements. And this is the way this can be implemented. So yeah, this is actually the scenario in which we have high output impedance. So we have an electronic circuit whose output impedance is extremely high, and we need to give the output of A to input of B. But the input impedance of B is low. So what would happen is that as soon as this, if we directly connect A to B, since here the resistance is low, the current will increase drastically, because here the resistance is high, so the current was low. But here, since the resistance is low, the current would be extremely high for the same voltage. So that might burn this circuit actually. And in order to avoid that, we connect A and B via op amp. And in op amp, the impedance, input impedance is extremely high, output impedance is extremely low. So there won't be any such scenario in this case. Okay, so now we come to the last part of this discussion, and I hope you have few more minutes, because one of you distracted the class in the beginning, so I would take few more minutes. And this is, I would say, this is the most important circuit that we would discuss. This is also the most interesting one, and this is known as the oscillator circuit. Have you guys heard about oscillators earlier or not?
Yes, sir.
It's a very brief discussion.
Sorry?
Sir, it was very brief in that transistor chapter in class 12.
Okay, so but by the way, what do you understand from oscillators?
So they provide oscillating voltage or current to the circuit.
Yes, that is one thing. Anybody else? Anybody else know that? What is an oscillator? Oscillators are extremely important circuits actually.
Sir, these decides the speed in some computers, crystal oscillators.
Speed in computers. Okay, so one of the most basic function of oscillators, as one of you pointed out, is that uh, it produces an output signal without any input signal, and it produces an oscillating output signal without any input signal. Now you might wonder, how can something produce output without any input? Can anybody tell how can uh,
Sir, crystal oscillators is a mechanical type of device in which quartz crystal oscillates and produce oscillation.
yeah, that's right. But is there any input signal to that or not?
No, sir.
Sir, can you repeat your question?
The question is, how can an electronic circuit produce output without any input?
Sir, by feedback.
Okay, by feedback. Yeah, that's right. But how?
Sir, if the output provides input to the circuit at just right time so that it continues to oscillate. So there is no extra input to the circuit.
But in order to oscillate, we need some kind of input as well. In order to oscillate at the first place, especially in the electronic circuits, yeah, we know that these crystal oscillators oscillate because of the or these atoms oscillate at non-zero temperatures because of the thermal energy. But how does that happen in electronic circuits? Okay, let's see that. It's actually the same kind of thing here. So oscillators is, in order to understand oscillator, we need to see what is oscillation. It is an effect that repeatedly and regularly fluctuates about the mean value. So there is a mean value, and about it, the signal fluctuates repeatedly and regularly. So the oscillating signal is produced. And oscillator is a circuit that produces oscillation. Oscillators are actually the signal generators. So if we need an AC signal, the sinusoidal signal or triangular signal, those are produced by oscillators. And the basic principle of the oscillator is it generally produces the output signal without any external input signal, except the DC input actually. So there is this DC input, because DC is required to switch on the devices. The basic principle is, the basic mechanism is uh, that oscillator is a combination of these three components: amplifier, filter, and positive feedback. So as Dikshant pointed out, that positive feedback is required, but in addition to that, we need an amplifier and a filter. So these three are required in order to make any oscillator actually, be it a mechanical oscillator or electronic oscillator. In mechanical oscillator, we would need a mechanical amplifier. In electronic oscillator, we would need an electronic amplifier. So as an amplifier, we can use the op amp, okay? But what is the role of filter and positive feedback? So the basic mechanism of the oscillator is that there is always a noise signal in the circuit, okay? And what is noise? Noise is a combination of various frequencies, lot of frequencies. Noise is just a random signal. But if we do the frequency decomposition, if we do the Fourier analysis, we would see that the noise signal has a lot of frequency components. Now what we do is that, and this noise signal is everywhere actually. At non-zero temperatures, if we are putting a battery across the device, it would be there. Or even electrons fluctuate at non-zero temperatures. At room temperatures, even electrons fluctuate and create noise signals. And noise signal contains a large frequency, large range of frequencies. Now what we do is, this noise signal is passed through a filter. And what is a filter? The filter is a circuit that allows certain frequency to pass through and disallows the other frequencies to go through the circuit. So what does the filter do? If a noise signal is applied to a filter, out of many frequency components, the noise will, this filter will only allow a certain frequency to pass through. Now, with positive, that signal is positive feedback and again passed through amplifier. So that's how that frequency is amplified. And again, because of this positive feedback, finally, only a single frequency or only the frequency that is passed through by filter is amplified, and that is what we obtain at the output terminal. Okay, so that is the basic mechanism. I'll uh, just restate it, that the noise travels around the loop and being filtered. After being filtered, it is re-amplified until it increasingly resembles the desired signal. So whatever signal we want, we will design that filter. We will design the filter that will allow that frequency to pass through. Okay. So now, before going into the oscillators, let's quickly talk about electronic filters. So this is the original signal. This is kind of a noise signal, and it's just a random signal. If we break this signal in various components, or if we do the frequency decomposition of the noise signal, this is how it looks like. So this signal will have a signal with low frequency, medium frequency, high frequency as well. So this is a combination of various signals of various frequencies. Okay. So this noise signal can be equivalently written as this signal, these combination of these signals. Now we have four kind of filters. One is the low pass filter, second is high pass filter, third is the band pass filter, and fourth is the notch filter. So the low pass filter only allows the low frequency signals to pass through. So if we apply or if we put all these signals at the input of the low pass filter, only the low frequency signal will pass through. Only this signal will pass through. If this is put as at the input of the low pass filter. Similarly, the high pass filter only allows the high frequencies to pass through, and it blocks all the other frequencies. So only this high frequency signal will be passed through the filter, and all the other signals will be blocked. The band pass allows a certain band of frequencies to pass through. It does not allow extremely low. It does not allow extremely high as well. So it allows only the medium kind of frequencies, medium frequency signals to pass through. So that this signal will be passed through the filter. And the notch filter disallows, it is like inverse of the band pass filter. So it allows the low frequency and high frequency, but it blocks the medium frequency. It is used in some applications, but it is mostly not used in oscillators. So only these three filters are prominently used in oscillators. One is the low pass filter, one is the high pass filter, and third is the band pass filter. Now, in order to make an oscillator, we need an amplifier. An amplifier we have actually, because transistor is an amplifier, op amp is an amplifier. We also know how to put a positive feedback in an amplifier. What we just need to do is we just need to design a filter. So if we understand how a filter is designed, it means that we can easily design an oscillator. So let's see how the filters look like, and we will only deal with very simple filter circuits, and those are the RC filter circuits actually. So if we just have this R and C in series with each other, a resistor and capacitor, the input is applied at the resistor and the output is taken across the capacitor. In that case, what happens is that if the input frequency is low, the capacitor will follow this signal, so output will be obtained. But if the input frequency is extremely high, in that case, the capacitor would not be able to follow the input signal, and the output will be zero or very low signal. So do you see this, that if the output is taken across the capacitor, and if the input voltage is a low frequency voltage, only then output will be obtained. Otherwise, the output will be zero. So this is a plot which plots the gain versus frequency. Gain means what would be the output as compared to the input. And for low frequencies, on the x-axis we have the frequency. For low frequency, the output is almost same as the input. But as soon as the frequency increases beyond a point, the output starts declining. And at very high frequencies, the output will be zero. The reason for that is that at very high frequencies, the capacitor cannot be charged and discharged according to the input. It will just remain the same actually, as we had seen in the full wave rectifier. Do you understand this?
Yes, sir.
Yes.
Yes, sir.
Yeah, so this is a low pass filter circuit, very simple low pass filter in which the output is taken across the capacitor. Okay, similarly, and this is the cutoff frequency. You might also be aware of this, that below this frequency, the capacitor would be able to respond to the input signal, and above this frequency, the capacitor won't be able to respond. Similarly, if we just swap the resistor and the capacitor and take the output across the resistor, this will become high pass filter. It allows high frequencies to pass through but blocks the low frequencies. What is the reason for that? The same reason actually. Because if there is a low frequency signal, the capacitor voltage will be identical to the input voltage. The resistor output voltage across the resistor will be very low. And if so, at low frequencies, capacitor follows the input, but at high frequencies, capacitor works like a open circuit. At high frequencies, this output across will be just the input, because no current is flowing, output is just equal to the input, but inverted. So this will be the gain versus frequency plot for this kind of circuit, and again the cutoff frequency is almost the same. And by using these two circuits in combination, we can design a band pass filter as well. So this is the high pass filter, this is the low pass filter. This C1R1 is high pass, C2R2 is low pass, and if we apply an input signal, this C1R1, this particular thing will block the low frequency components, and then that output of this high pass goes to C2R2, and it blocks the high frequency components. So that way only a medium frequency range will be allowed through the circuit. So this is at this link you can find more about RC filter circuits. This is also available in many standard textbooks, so you can figure that out. So in order to make a band pass filter, we just need to design the cutoff frequencies of these two filters such that the cutoff of the high pass filter is uh, less than the cutoff of the low pass filter. Okay, that way only the band pass will be allowed through this circuit. So just go to this link and you can find more about it. Now let's see how an oscillator circuit will look like. There is one more point that we need to keep in mind, and that is that if we apply an input voltage in this kind of circuit, let's say in an RC circuit, the output voltage is actually not the same. Output voltage has a phase difference with respect to the input voltage. That is because of the capacitance, because capacitance needs finite time in charging and then in discharging. So the output will be slightly lagging, or output will have slight phase difference as compared to the input voltage, or it will be leading sort of in this particular circuit. Do you know this fact or not? Do you
Yes,
know that
sir.
the output
Yes, sir.
across an RC circuit has a phase difference with respect to input? Yeah, so that's what we also need to keep in mind in filter circuits. So now with this knowledge, let me say that this circuit is an oscillator circuit. This is an oscillator. But how does this circuit act like an oscillator? This part of the circuit, this shaded part, what is it? It is, can anybody tell?
Amplifier.
Inverting amplifier. You're right, it is an inverting amplifier. Second, what is this?
Filter.
Yes, this is filter. But why do we need three such filters? Because as you see we have three RC circuits, three filters in series with each other. That's the key point here. So in addition to amplifier and filter, we need positive feedback. Okay. We need to make sure that the output is going through the amplifier with positive feedback, and this is the output terminal. There is, as you see, there is no input voltage applied in this circuit. Just the noise is getting amplified and filtered, and it will produce a signal. Now, what is happening is that each of these RC circuit is having a phase difference of 60 degrees. So the three RC circuits will have a phase difference of 180 degrees. Okay. So when a signal which comes here and when it passes through these three circuits, the total phase difference between this point and this point is 180 degrees. Again, this signal is sent to the op amp where it is applied on the inverting terminal. Again, 180 degrees phase difference is there here. So in total, if we see the phase difference between this point and this point, it is 180 degrees here and 180 degrees here. In total, 360 degrees. So positive feedback. Okay. Is this point clear? Not, because this is the, I would say this is the crux, the key point here.
So can we choose positive non-inverting part of the op amp, and then we can adjust the phase difference of this RC circuit by choosing?
Yes, exactly. Yeah, that's always the case. We can do that, but again, for three, so we ultimately we need 360 degrees of phase difference, and so we would need to use as many circuits as would produce 360-degree phase difference, and in that case, we can apply this output to the non-inverting terminal. Okay, we just need an amplifier and a positive feedback along with the filter, and rest freedom is with us. We can do it the way we want it to be done. Generally, in this combination, if there is a 60 degrees phase difference, in order to produce 360 degrees, we need 6 RC circuits. So it becomes a huge, it becomes more number of components. So that's why 180 degrees phase difference, which is inherent in the op amp. Okay, so this is one example how using an op amp we can implement an oscillator basically. Okay, so that's all I wanted to discuss about electronic circuits. Although if there would have been more time, we would have discussed a bit about the digital circuits as well. But I realized that that there is a full course on digital electronics, maybe in your next semester. So you would know that in greater detail in that course. Okay, so that's why I just wanted to highlight the important parts of the electronic circuits here. So this essentially completes our discussion of electronic devices and a very brief summary of various electronic circuits, mainly analog circuits. So I will share this slide and just go through the slides and work out all the examples, all these circuits. That will give you a proper idea. Okay, and if you have any doubt, you can get in touch with me. And this will also be the subject matter of the NSEM. So in NSEM, whatever Professor Ghosh is teaching, that will be there, and some part will be there from from the entire part that I have taught.
So what type of question will be there from this last part?
Yeah, so these the questions might be based on these circuits, the circuits that we have seen here. So that's why I am repeating that. Please work out these circuits on your own. Please make sure that you understand how that you understand these expressions, how these expressions are coming about. Okay.
Okay, sir.
Okay, so that's all for the day. I'm sorry for taking a bit longer time. And thank you all. It has been a pleasure to interact with you. And I hope your course projects are also going on, at least. Although I understand that being at home, it's not an ideal situation to do a course project, but still you can do quite a lot. And the course projects are meant for your own understanding. It's not to put pressure on you. It's for enhancing your understanding of things, especially the electronic components. Okay. So that's all. Thank you, all of you.
Thank you, sir.
Thank you,
Thank
sir.
you, sir.
Yeah.
Thank you, sir.
Thank you, sir.
Yeah. Maybe see you in coming semesters. Yeah. Bye bye.
Thank you, sir.